Hi everyone, and welcome to the first of two videos looking at some past exam questions on the topic of rate constants and temperature. Now, this is a topic that often people find quite difficult. The theory behind it is quite complicated, but in terms of the actual exam questions themselves, they are actually pretty straightforward in terms of what you actually have to do with that theory is quite simple, and it does usually turn out to be the same thing every time. And most of the difficult concepts behind it, you don't actually need to worry about too much. This topic is basically looking at how does temperature affect the rate of reaction. Everything we've looked at so far in terms of orders of reaction has always been about linking the rate to the concentration, whereas this is about looking at temperature. And so it's focusing on the link between the rate and the rate constant. In this question here, what they're trying to do is the student has carried out an investigation to try to find the activation energy. And that is usually the aim of this type of question, is to work out what the activation energy for the reaction is. Okay. And they will have done some experiments, and they've given you your data in a table. Now, this data initially looks a bit intimidating. You've got all kinds of strange things going on. We've got 1 over temperature. We've got kind of horrible looking numbers in standard form. We've got logarithms involved. It looks kind of horrible, okay, but it's not too bad once you know what you're doing. The reason behind having all of this information is because of the equation, the Arrhenius equation, that links the rate constant and the temperature together. Okay, and the good news is that is not an equation that you are needed to remember. It is on your data sheet that you get given in your exams. Okay, just to prove it to you, they do give you the equation that you need. So your Arrhenius equation is here. This format of the equation, very rarely you need to use. It gets rearranged into this format, and this is the format that involves plotting the graph, and this is the format that all the questions refer to, but it is given to you, so it isn't something that you need to worry about learning. And once you see the equation in this format, you can understand why we've got some of this slightly strange information in the table. You can see where the logarithm of k fits in. And you can see why we've got 1 over T, because we've got 1 over the temperature in this equation. Okay. As I said, don't worry too much about this in terms of what we actually have to do. You'll see it's fairly straightforward. So what do we need to do? We need to add the missing values to the table and then plot a graph, okay, on the graph paper, which I'll show you in a second. And then use the graph to calculate the activation energy. That's the aim, and that's usually the aim of this type of question, as we said. So we need to fill in these missing values. This value here is 1 over T. So that just means it's 1 divided by the temperature. And the temperature is in Kelvin. So this is actually really straightforward. We just need to do 1 divided by 290. And we're getting a kind of horrible number here. We want to put it in the same sort of format as we've got here. So something times 10 to the minus 3. So this is going to be 3.45 by the time we've rounded it up. Okay, times 10 to the minus 3. Okay, and then we need a value for natural logarithm of k. Now, again, you may not be familiar with logarithms, but this could not be simpler. It says ln k. There is an ln button on your calculator. So you press that and you type in what the value of k is. So in this case, the rate constant is 1.99 times 10 to the minus 4. So even if you're not super familiar with the maths here, it's actually really easy. Okay, and we're getting minus 8.52. If we do it to 2 decimal places, the same as all the other figures here. And then just before you go any further, just look at the values that you've calculated and think, does that seem sensible? Does it fit in the pattern here? You can see the numbers are decreasing. 3.45 seems sensible. And you can see the pattern here, minus 13, minus 11, minus 10, minus 8, minus 6. Okay, that seems like it's in the right kind of pattern. We've probably got that right. You know, if this comes out as minus 22, you should be looking at that and going, something's gone wrong here. Okay. So we filled in the values. Then we need to plot a graph. I've done that already because you don't need to see me plotting some points on a graph. But I do want to just make a point about the line of best fit with this. You do actually need to take a bit of time to get your line of best fit as accurate as you can, because if you're slightly out on the gradient, it does actually make quite a big difference when you come to do the calculation. So it is worth taking a minute to try and get your line of best fit as good as you can possibly get it. Just a quick tip, the problem I always find with a line of best fit, if you've got a ruler, is you put your ruler on and you can't see any of your points anymore. And so it then becomes difficult to draw your line of best fit. Sometimes it's quite nice to put your ruler on its edge and to do it that way, because then you can still see the points. Okay, hope that's coming out okay on the video. And it might be easier to do it that way. I'm just going to go ahead and put this on here. So you draw your line of best fit. Okay. Then if we go back to look at our equation here that they give you on the data sheet, the reason that we've got the equation in two different forms is that this form of the equation is the form of a straight line. It's in the form y equals mx plus c. Okay, you can see on your graph that you've got the natural logarithm of k on the y-axis. So that is your y part, and you've got 1 over t on the x-axis. So I'm going to write this equation out again here, just so that we've got it. And I want to show you that that is actually in the format of y equals mx plus c. And to get it into that format, we just need to change this slightly. Okay, this is our y value, but you can see that our x value is 1 over t. So I'm just going to separate out this term, and we're going to write it as minus EA over R times 1 over t. Okay, and then hopefully you can see then that that is in the format of y equals mx plus c. Okay, this is our x value, this is our y value. Why is that helpful? Well, because m and c actually represent things. Okay, m is the gradient of the graph, and c is the y-intercept. Now, we want to calculate the activation energy. Okay, so we're looking at this term here. So the bit of our graph that we're interested in is the gradient. Okay, so that's the next thing we're going to go ahead and do. We're going to calculate the gradient of our line of best fit that we've done here. Okay, it's always a good idea when you're doing a gradient to do it as big as possible. I often see people trying to calculate a gradient with a little triangle here. Use as much of the graph as you can. Okay, so I'm going to go for a nice big triangle. I'm just going to use my points, actually, because then rather than trying to read off what the values are, if I use this point and that point, then I know what the values are because I've got them written in the table. Okay. So if we just go ahead and draw ourselves a triangle here. Okay, then we know our change in y. If I get the values back again here. So the y value for this first point, we're looking for the natural log of k. So the y value for the first point was minus 6.57. So our change in y is minus 6.57 minus, and then this was 13.41. And our change on the x is from 3.1 times, you can see that, 3.1 times 10 to the minus 3. Okay, be super careful here if you're just looking at your graph. And this is one of the other reasons why if I actually go back to the table, you can find the actual correct values. So we're going from 3.1 up to 3.6. Okay. So I can shortcut that and we can say it's 0.5 times 10 to the minus 3. Okay. So if we then calculate our gradient, what does this come out as? That's our change on the y-axis divided by 0.5 times 10 to the minus 3. Okay, and we get a value of 13,680. But of course, looking at our line, the gradient is negative, isn't it? Okay, we can see we've got a negative gradient. So the gradient is minus 13,680. Well, the gradient is represented by m, and from our equation, m is minus EA over R. Okay, so therefore, minus 13,680 is equal to minus EA over R. Okay. R is a constant. It's a gas constant, and again, that is also given to you on your data sheet as 8.314. So now all we need to do is just multiply by that value. Okay. So we're going to take this and we're going to times it by 8.314. And we're going to get a value of 113,735.52. Now, that should be minus, shouldn't it? So if we've multiplied by R, minus this value would be minus EA. So actually that value is just the activation energy, isn't it? Okay. And then the only thing that we need to do now is that this value is in joules, and we need to get it into kilojoules. So we just need to divide by 1,000. Okay. Does it say in our question anything about doing it to the right number of significant figures? No, it doesn't mention it at all. Okay, so we don't need to worry about it. So in terms of turning this into kilojoules, we're just going to divide by 1,000, and I'm going to call that 114. Okay, and that's it. Okay, so it seems like there's a lot of complicated stuff there, but if you actually go back to this question and think, what have we done? You calculated some values by just putting them in a calculator. That wasn't difficult. We plotted some points and drew a line of best fit and calculated a gradient. That's not difficult. And then you use your equation which you've been given. Okay, and so then what did we actually do? Well, we calculated the gradient, and then we just times it by 8.314, didn't we? And got rid of the minus sign and divided by 1,000. And actually that's all you need to do. So although this looks kind of horrendously complicated, it is actually fairly straightforward once you get used to it. The only thing to watch out for as well is, do watch out for the minus sign. If you're thinking about your answer, it doesn't make sense to have a negative activation energy. Okay, remember, the activation energy is the energy needed to start the reaction. The energy needed to start the reaction can't be minus 114. That doesn't make any sense. So just be sure that with your activation energy that you do always have a positive value. Okay.